Okay, so in this video we'll talk about Poisson distribution. So our topic is Poisson probability distribution. Now before writing out explicitly the formula for the Poisson probability distribution, let us motivate the how the distribution might arise. Let us give an example of an experiment. Suppose there is some experiment. In this experiment, there are some photons that are emitted from the experiment at random interval, and we have a detector that detects photon, and whenever a photon reaches the detector gives a click. So we have a counter attached with the photon. So this is the detector where the photon hits, and this is the counter by which we count the number of clicks. So whenever a photon is reached, the value of the counter is incremented by 1. Now we can review a few assumptions about the experiment. Number 1, the photons are emitted at a random interval and there is no memory associated with it. That means suppose kth number of photon is emitted, then the probability of getting the k plus 1 photon doesn't depend when the kth number of photon got hit. So each of these hits are independent event. So each clicks or hits are independent event. So this is our number 1 assumption. Number 2 assumption is at a given instant of time there are only a single click. So fix a instant of time. At this time it is not possible to get 2 photons in the detector or get 2 clicks in the detector. So at a particular instant only one photon can hit detector. Now with this assumption, our interest is to calculate the Poisson probability distribution. Now what is Poisson probability distribution? The Poisson probability distribution Pn of t, it is the probability that n clicks happens in time t. So this is our target probability distribution which we want to derive. Now here t is the time and n is the number of clicks. Okay, so how do you derive this thing? So first let us calculate Pn t plus dt. What is Pn t plus dt? It is the same as the probability that n clicks happens in time t plus dt. So to derive the Pn t plus dt, we see that we have to take into account 2 events. The event number 1, E1, let's call it E1. E1 is that n number of photon arrives in time t, and in time t to t plus dt no photon arrives. So let us draw a line and let us call it time axis. So it is 0 time axis. So it is 0, this is t plus dt. Okay, so as we discussed, one possibility of event, that is E1, is n photons arrive in time t. Here this second part is no photon arrived. Now there is another possibility to get the n number of photon in time t plus dt, that is event 2. Event 2 is similarly as event 1, but here we have number of photons is not n but n minus 1. So we have n minus 1 photons arrived in time t, but just one photon arrived between t and t plus dt within dt time. Now the total probability Pn t plus dt is the sum of P of E1 and P of E2, because if either event 1 and event 2 occurs, we get the desired result that n photon has arrived in time t plus dt. Now P of E1 has two parts, that is n photon has arrived in time t multiplied, because they are independent event, that no photon arrived in time dt. So what is the probability that no photon arrived in time dt? Well, to determine the probability of no photon arrived in time dt, we must introduce a parameter. So we introduce a parameter lambda. Lambda is defined as probability of a click in the detector per unit time. Okay, so in time dt, what is the probability of getting a click? So it is lambda dt. So what is the probability of not getting a click? It is simply 1 minus lambda dt. Now these two events are multiplied because they are two independent events, that what our number one assumption was. So therefore we get P of E1. Now let's drag this thing to calculate P of E2. So we have P of E2. So what is P of E2? P of E2 is nothing but getting n minus 1 photon arrived in time t. So the probability is P n minus 1 t multiplied by 1 photon arrived in t plus dt, lambda dt. Okay. Now one may ask a question that in time dt, why don't you consider 2 photon arrived? Well, answer is we can make dt sufficiently small so that only one photon can click within dt time. Okay, so this is the reason why we have not taken into account that 2 photon can arrive between t and t plus dt. So now we have Pn t plus dt equal to p of e1, which is p nt into 1 minus lambda dt. So let's write it, pn of t into 1 minus lambda dt plus this term p of e2, which is p of n minus 1 t lambda dt. Now we can rearrange the term to get the equation pn t plus dt minus pn t by dt equal to minus lambda pn t minus pn minus 1 t. Okay, now this quantity is nothing but pn prime t defined as dpn t by dt. So we have pn prime t equal to minus lambda pn of t minus pn minus 1 t. So this is the differential equation, or we may call it recursive differential equation, that we need to solve in order to get pnt, that is the probability that n photon has arrived in time t. Okay, so before solving this equation, we note few initial conditions. Okay, the first one is, what is p0 at t equal to 0? What is the probability that no photon arrives at t equal to 0? Well, it is a certain event, because as soon as you start the experiment, you don't get click. So this is p0 at t equal to 0 is 1. Now what is the probability that p of k at t equal to 0, where k greater equal to 1? Now this is 0, because as soon as you start the experiment, you don't expect a click. Okay, so these are the two initial conditions. Now we have to take care of one more condition, which is p minus 1 at t. Now this is 0, because it is a nonsense question that at any time there is some negative number of photon hitting the detector or get a negative number of click. So this is 0. So let's start with p0 t. Now from the differential equation, we have p0 prime t equal to minus lambda p0 t minus p minus 1 t. Now this part is actually 0, so we have p0 prime t equal to minus lambda p0 t. Now this equation with the initial condition that p0 at t equal to 0 is 1, this gives the solution p0 t equal to e to the power minus lambda t. This looks like exponential distribution. Okay, thank you.